Okay, so last time we talked about limits at infinity, and I briefly mentioned that the way in which we can find limits at infinity is similar to how you might find horizontal asymptotes. So there is, of course, a connection, and it turns out as long as a limit at infinity exists, there is going to be a horizontal asymptote. So let's look at the following rational function here, and a general rule that's oftentimes introduced in a pre-calc class is that to find horizontal asymptotes of a function like this, what you want to do is you want to consider the degree of the polynomials in question. So as a reminder, the degree is going to be the value of the largest exponent of the top and the bottom. Or should I say that's going to be the degree of a polynomial. A rational function is consisted of a polynomial divided by another polynomial. And the general rule that was seen is if the degree of the numerator was larger than the degree of the denominator, so if the degree of the numerator is larger than the degree of the denominator, there was no horizontal asymptote. It actually turns out that we have a slant asymptote here, which occurs because the degree of the numerator is 1 more than the degree of the denominator. But for purposes of this class, we're not going to worry too much about slant asymptotes because ultimately we're trying to find limits. So in this particular example, we would see that the limits of f of x, so the limit as x approaches, and this is true for both, well, I guess it's different for plus and minus infinity, but for plus infinity, it's going to be infinity, and for negative infinity, it's going to be negative infinity, as we can see by the graph here. With this example here, it's pretty much very similar type of problem, except this time the numerator has a larger degree than the denominator, so the degree of the numerator is less than the degree of the denominator. We saw that the horizontal asymptote was actually 0, which you can see by this graph here, which of course also indicates to us that the limits as x approaches plus or minus infinity of this function here is going to be equal to 0. And in this case, it doesn't matter whether it's plus or minus infinity. That's going to be the case. And finally, if the degree of the numerator and the degree of the denominator were the same, so that is to say that those two numbers are equal, then the general rule here is that you look at the lead coefficients here, and we know that the horizontal asymptote will be the ratio of the lead coefficients, which we can see in the graph of the function here. We'll see that the horizontal asymptote is actually at y equals 2. And that, of course, indicates to us that the limit as x approaches, and again, this is both true for plus and minus infinity, of our function is going to be 2. So we can actually use these rules to figure out what the limit is without necessarily having to do the thing where you find what's the highest exponent and you divide each term. You can still do it that way. You'll get the same answer. So one way that we can summarize this rule is with the following rather complicated looking expression. And this summarizes all three rules together very easily. If we have something that's rational, and again, a general polynomial looks like this, divided by a general polynomial. Notice that n is the degree of the numerator, and m is the degree of the denominator. So the degree of the numerator is going to be n, the degree of the denominator is going to be m. To find this limit at plus or minus infinity, all we do is we're basically going to take the ratio of the lead coefficients here, and we're going to multiply it by the limit as x approaches either plus or minus infinity of whatever the difference in the lead terms is. And obviously, if the degree of the numerator is bigger than the degree of the denominator, then this is going to become the limit. So degree of the numerator is bigger than the degree of the denominator. This is going to be of the form x equals plus or minus infinity of x to the n. And we showed, and then the a over n and the b over n don't matter because this is going to be plus or minus infinity. And that will, of course, depend on whether n is even or odd, as we saw in the last example. If the degree of the numerator is less than the degree of the denominator, then we know that this is going to kind of look like a over n over b over m times the limit as x approaches plus or minus infinity. But this time it's going to look like something like 1 over x to the n. And again, n is not the same n here. I probably should use like some value p, for example, just to show that it's not n or m. In which case, this is going to be 0. And again, just like before, the a over n and the b over m won't matter. And then if they're the same, when you take their difference here, you'll have a over n, b over m. You'll have the limit as x approaches plus or minus infinity. And here we'll have x to the, well, n and m are the same, so that's x to the n minus n, or x to the 0. So this thing just becomes 1, and then that resorts to whatever this lead coefficient is. So this little formula here kind of encapsulates all three cases that we saw earlier. So let's apply this to a couple examples, and we'll see how this works. Okay. So in this first example here, we're taking the limit as x approaches infinity of 20x squared over 3x to the fifth. We can just immediately determine, since the degree of the denominator is larger than the degree of the numerator, we can simply say that this is going to be 0. Okay. Again, we can use this formula, but in this particular example, it really doesn't matter. If they are the same here, we just consider the ratio of the lead coefficients. Again, I don't care about anything else in the problem. That stuff doesn't actually matter. I'm not saying that this cancels. It's just irrelevant for the sake of the problem. I know that this is going to be 20 thirds. So very simple. Again, it doesn't matter whether it's plus or minus infinity. In this last case, though, things are a little bit different, and actually the formula will be helpful, especially if we want to make the distinguishment that this is either plus or minus infinity, because we'll see that this is actually going to be equal to the limit as x approaches negative infinity of 20 over 3. Actually, I should probably bring that outside. Actually, it doesn't even matter because it's going to be infinity. So this is going to be x to the 7 minus 5. So this will be the same as the limit as x approaches negative infinity of x squared. And because 2 is an even number, okay, and we're taking this as x approaches negative infinity, remember that something with even symmetry, or something that's an even function, will have y-axis symmetry. That's an easy way to remember this. So I know that as x approaches negative infinity, this function is actually increasing in an unbounded way, so it should be positive infinity. And as I said, technically there is a 20 over 3 out in front here, but 20 over 3 times infinity is just infinity, so that doesn't matter. I suppose one thing where it might matter is if this was a negative sign here. So I guess it's something that you do want to consider, but that's how we can take limits of rational functions. As always, I hope that you found this video helpful, and take care.